Today we're going to cover writing exponential equations into logarithmic form. But before we do that, we have to review exponential properties. Okay, and this will help you for the math, the NCBI 0324. Okay, here we go. So this is a topic that we're going to cover today. Exponents, radicals, and logarithms. Exponent properties will be the first one, and then converting radical expressions to exponential expressions and vice versa. Simplifying radicals, exponential function graphs, writing exponential equations to logarithm equations and vice versa, logarithmic functions, and finally, application problems. So this is topic number one, exponent properties. This here is like the concept, okay? It says if m and p are integers and a and b are real numbers, then this will take place. This is called the product rule, which means if you have a to the m times a to the n equals to a to the n plus n. In other words, the a is called a base. When you have the same basis and you're multiplying a base to an exponent times a base, same base to an exponent, you add the exponents. This is called the quotient rule. Again, if you have a to the m divided by a to the n, it'll be the same base, but you subtract the exponents. And a cannot be 0, because if it's 0, it'll be undefined here at the on the denominator. This is called a power rule. If you have a base to an exponent raised to another exponent, or a power to a power, you multiply the powers. The exponents. The power of the product rule. If you have a times b to the n power, then it'll be a to the n times b to the n. And I'll be giving examples of each one of these. Furthermore, if you have a to the m times b to the n, it will be a to the m times p times b to the n times p. The power of the quotient rule. If you have a divided by b, right, to the power of n, it will be a to the n divided by b to the n. And furthermore, b cannot be 0. Also, if you have a to the m divided by b to the n, all raised to the p power, it will be a to the m times p divided by b to the n times p. The negative exponent rule. If you have any base to any negative power, you have to make it positive by put 1 over a to the n, and the n becomes positive. There's a lot of these rules that you'll be using in the upper level courses, so it's good to know them. Also, if you have a divided by b to the power of negative n, all you do is go on the fraction, and the exponent becomes positive. This is called the zero exponent rule. Any base, right? My a is a base. Any base to the 0 power will always be 1. And finally, fractional exponent. If you have a base to the power of m divided by n, the n becomes your index, the a becomes a radicand, and the n becomes your exponent. And furthermore, this will be easier to simplify without a calculator. These two are the same formulas here. But the only difference is at first, you're going to take the nth root of a and then raise it to the n power. Okay, now let's begin with some examples. Okay, first of all, this is a product rule number 1. Right, a is the base and m is the exponent, like I mentioned earlier. Must have the same base to example, right? This feels like the concept, guys, right? But you're not going to do it this way because this will be too long. So in other words, it's better to use the rules. And that's why I put x cubed in blue times x squared in green. Right? So x cubed is the same thing as x times x times x. And x squared is the same thing as x times x. So x times x times x times x times x 5 times will give you x to the 5th power. But it's better to apply the rule, right? You have the same base, x and x. You do without the exponents. It'll be x to the 5th power. Okay, this one here, x to the 7th times x to the 3rd, right? They have the same base. So it'll be x to the 10th power by adding the exponents. x squared times y squared. These are not the same base, right? Not the same base, so they stay how they are. X squared times y squared is your answer. Here we have parentheses 5x to the fourth power, close parentheses, times parentheses negative 3x to the second power, close parentheses. So here, guys, we're going to multiply the coefficients, which is 5 times negative 3. And then it'll be the right, because they both have the same base, the x, and we add the exponents. So it's going to give us negative x to the 6. Not even here, right? Here we have parentheses negative 2 x to the fourth power y cubed, close parentheses, open parentheses, times negative 3x to the fifth power y squared, close parentheses, is equal right here. It'll be the same thing as number 4. But the only difference is that we have another variable, which is a y. So in this case, it's going to give us negative 2 times negative 3. And then we have x on both of them, x to the fourth, x to the fifth. So we're going to add them. We have y cubed and y squared. So we're going to add those. So my answer is going to be 6x9 to the ninth power, y to the fifth power. You can go straight from here, from the original problem, to the answer. The middle part is just to show you how we got 6x to the ninth power, y to the fifth power. Now here, right here, we can go. Let me go back real quick. Here we can go straight to the answer, right? Negative 5 times 6 is negative 30. X times x cubed will give us x to the fourth power. And the 6x cubed doesn't have a y, right? So it'll just be y cubed. So this is my result. Negative 30, x to the fourth, y cubed. Number 7, right? 3 times 3 times 8 is 24. X to the fourth times x to the fifth will give us x to the ninth. And y cubed times y to the first power will give us y to the fourth. There's my result. Now comes rule number 2, which is a quotient rule, quotient and power rule. Now you see you have the same base, right? A to the m divided by a to the n. We subtract the exponents. Example, same base, it'll be x to the power of 5 minus 2, which will give us x cubed. X to the 10th divided by x to the 7th. Again, they have the same base. So it'll be x to the third power, because 10 minus 7 is 3. X to the fourth divided by x to the 8th. Again, they have the same base. So it's going to be x to the negative 4. Later on, they don't want you to leave it as negative, right? So later on, when we do the negative rule, right, it's going to be 1 over x to the fourth power, but we're not there yet. Okay, so I'll explain that later. Okay, there we go. You see, rule number 6. This is called the power rule. This is rule number 3. If you have base a to the power of m, everything raised to the n power, we multiply the powers. It'll be a to the m times n. Example, x cubed times x cubed to the power of 2 will give us x to the 6th power. But anyway, this is, also the concept. Without the rule, they'll give us x cubed times x cubed, right? Then we apply the power rule, which would be x times x times x 6 times, so will give us x to the 6th power. But it's better to use a property, right? By using the property, we eliminate all this work here. So it'll be x to the power of 6. It will give us, right? Here is where it gets a little bit tricky with a negative sign, okay? But check this out. Let's expand it first. The answer is x to the 8th, but let me tell you why. X to the 4th squared is the same thing as x to the 4th. Negative x to the 4th times negative x to the 4th. So negative times a negative will give you a positive. And then x to the 4th times x to the 4th times x to the 4th will give us x to the 8th, because 4 plus 4 is 8. Here's the key for you guys to always get the signs right. You see this whole thing instead of the parentheses, right, is negative. When you raise it to the even power, the answer is going to be positive. If the power was odd, it's going to be negative. Okay, I repeat, because it's even, the answer will be positive. If the power on the outside was odd, then the answer will be negative. Okay. For example, this one here. right? It's negative, so we know it's going to be, that's going to be negative. But it'll be negative y to the 6th power. But first, let's expand it. Okay. Is equal to negative y squared times negative y squared, which will give us y to the 4th power, because negative and negative will give you a positive. Y squared times y squared will give us y to the 4th power. And then we multiply by another one. We multiply by another one because it's to the 3rd power. So this becomes negative y to the 6th power. But you can go straight from here to the answer, right? If you know the properties. Now comes the power of a product rule. Okay, by applying the power here, number 14, it's going to give us x squared times y squared. This will give us 8x cubed, because it's 2 cubed times x cubed will give us 8x cubed. This will give us x to the 6th, y to the 8th. Why? Because we're multiplying the powers. We have a power to a power, so it'll be 3 times 2 is 6 for the x, and 4 times 2 is 8 for the y. Okay, now look at this one here, okay? Remember, it's odd, right? It's odd, everything raised to the odd power, and it's negative, it's negative, so it's going to be a negative answer. This will give us negative 27, x to the 6th, y to the 3rd. Why? Because negative 3 to the 3rd power will give us negative 27. X squared to the 3rd power will give us x to the 6th. And y to the 1st power raised to the 3rd power will give us y to the 3rd power. But here's how we can simplify it further, right? It's going to be negative 3x squared y 3 times by itself 3 times. You see, negative 3 times 3 will give us negative 27. X squared times x squared times x squared will give us x to the 6th. And y times y times y will give us y to the 3rd power. Okay? All right, or we can do you see there's different ways to get the answer. There'll be negative 3 because the exponent on 3 is 1, right? Because there's nothing there, we know it's a 1. So 1 times 3, x to the 2 times 3, and y to the 1 times 3. Will give us negative 27, x to the 6th, and y to the 3rd power. There's always there's different ways you can get the answer. It's up to the individual student to see what's better for them. Okay? This is the power of the quotient rule. Right? By applying the rule here, it's going to be x cubed over y cubed. Okay, now look at this one here, right? It's going to give us x to the 10th divided by w to the 15th. Rule number 6. This is a negative exponent. Okay? For example, x, right, by applying the rule, it'll be 1 over x to the 5th power. 3 to the negative 2 is going to give us 1 over 3 squared, which will be 1 over 9. Okay, now, if we have a fraction, right, raised to a negative power, what you do is you flip the fraction and the power becomes positive. Right? That was a rule that I showed you, I think, on the second slide. So they will give us y cubed divided by x cubed. Okay, let me show you how then, okay? Right, if you apply the rule, right, it becomes positive. Now, this will be 1 times, the second fraction, you have to flip it. See, same thing. But it's better to apply the rule. But here's like the concept how to get the answer. But you can go straight to the rule and you can eliminate all this work here. Okay, here guys, let's apply this rule here, guys, right away, right? So we're going to flip it and it becomes positive. So it's going to give us 25 over 4. Now comes rule number 7, the zero exponent rule. If you have a to the 0, it will, will always be 1, and a cannot be 0. So x to the 0 will give us 1. Parentheses 5xyz close parentheses to a 0 power is going to give us also 1. Let me go back real quick. Yeah, that was the last one, right? In other words, anything raised to a 0 power will always be 1. Always, always, always. Now comes rule number 8, the fraction exponential rule. If you have a base, right, my a is a base, raised to a power of a fraction, then we have to convert it from exponential into a radical. So the end, right, which is the denominator on the fraction of the exponent, is called your index, which would be like the nth root. A is a radical, and the m will be the exponent on the a. Furthermore, this is easier to simplify. Parentheses, the nth root of a, close parentheses, to the power of m. Okay. Again, the n is called the index, the a is called the radicand, and the m will be your exponent, which is your numerator. Okay. Radical symbol. Again, right, so there it is. Now just right here. I want you to convert from from exponential into a radical. So right, so it's going to be, the 3 will be my index, the x is the radicand, and here guys, right, we don't have to put a 1 there because we know that x to the first power would just give us x. Now this is going to give us, right, it's going to give us the 5th root of x cubed. See, because the denominator on the power on the fraction, will be your index. Again, x is your radicand, and the numerator becomes the power. Again, same thing, right? So it's going to be the cube root of 3w to the second power. A common mistake that students make here is that they don't put the parentheses, they just put 3w to the second power, which is wrong, because both the 3w are squared. If you don't put the parentheses, it's just saying that only the w is squared, which is not correct. Now you have to go the other way, right? So this will be my base, right? The base is your a. The n is a 7, and the m is a 2. So it's going to be parentheses 8xy close parentheses to the power of 2 over 7. Okay. Just for this one here. This will be a 6x, right? The 6x is together, so it's going to be with parentheses to the 1/4 power. This is your answer. Now here's where people make some mistakes here, common mistakes. You see, they go from here to here, which is not correct. Because here, guys, they're saying that only the x is to the 1/4 power. But the thing is, in the beginning, guys, right, we had 6x. That means that the whole thing, the whole 6x is your radicand. That's why, please do not make that mistake. Okay, now simplifying radicals. Okay, before we simplify radicals, radicals are different roots. For example, it could be square root, cube root, or fourth root, or a fifth root, or so forth. Now, before we simplify these, you have to know basic stuff. Okay, you have to know basic square roots. For example, the square root of 1 is equal to 1. The square root of 4 is 2. The square root of 9 is 3. Right, and so forth. At least know all the way to 12. Or at least 10 to 100. For the cube roots, right, at least know all the way to, I think, to 5. You see? And then for the fourth roots, at least know all the way to, I believe, 2 or 3. I think it's 3. That's it. At least know these right here. Okay? Okay, now, here we go. How to simplify a radical. So you have the square root of 24. Right, the square root of 24 is not here, which means, let's see if it can be simplified. So what do? You see 24 is 24 a perfect square? No, it's not, right? So we have to we have to get the factors of 24. Right, these are the factors. 2 times 12, 3 times 8, and 4 times 6. Okay, now from all these, okay, not including 1, which is a perfect square? If you notice, we know that 4 is a perfect square because the 4 is here. So we're going to convert from the 524, which is the greatest perfect square, will be the 4, right? So we're going to use the square root of 24 is equal to the square root of 4. 4 times 6, which means the square root of 4 times the square root of 6. The square root of 4 is equal to 2. So this is my simplified version of the square root of 24. And a lot of students have a hard time with this in the upper level classes. Okay, so please try to know the foundation now that you're taking the 0324 with the 1324. Okay, now we're doing exponential functions. Now these, now from here on, is really from 1324. From the previous slide to the beginning, right? From the beginning to the previous slide, it's like 0324. But it's always good because you're going to be applying some of the rules in this course and also on the 1324 course and also on the 1325 and so forth. So it's good to refresh on the exponent properties. So examples of exponential functions, right? So these are called exponential functions. And why are they all called exponential functions? Because the exponent is a variable. If you notice, it's an x, or it can be a y, or it can be any variable. That's what it means. It's an exponential function. Okay, remember we call a is the base, and the exponent, the exponent will be the x, which is called a variable. Now, right, so this is a function here that we're going to try to graph. Okay, now, first of all, before we graph, we're going to have to evaluate the exponential function. When you try to graph, you always try to get numbers from -2 to about 2 or 3. These are the values for x that you will always use. Okay? Most of the times, like 99% of the time, you will use these because it'll make your work much easier. Okay, now, so how do we do this? We're going to evaluate the function at -2, right? And -2, and then -1, 0, 1, 2, and 3. So let's first start with -2, right? So f of x, this is my function, f of x equals to 2x. So to evaluate when x equals to -2, we're going to evaluate it f of -2, which means I'm going to plug in -2 where the x is. So now here, guys, we're going to apply the negative exponent rule, which will give us 1 over 2 squared, which will give us 1/4. So when x is -2, my y is 1/4. Now let's try -1. Right, so same thing, right? Because the exponent is negative, we're going to use the negative exponent rule. This becomes 1 over 2 to the first power, which will be 1/2. So when x is -1, my y is 1/2. Now let's use 0 now. Remember, now we're going to use the 0 property rule for the exponents. Anything to a 0 power will always give me 1. So when x is 0, my y is 1. Now let's try 1. When x equals 1. Which means f of 1 means it's going to be 2 to the first power, which will just give us 2. So when x is 1, my y is 2. Now let's try when x equals 2. We're looking for f of 2, which will be 2 to the second power will give us 4. So when x is 2, my y is 4. And lastly, let's use 3 for x. So when x is 3, we can evaluate it f of 3, which will give us 2 to the third power, which will give us 8, because 2 times 2 times 2 is 8. So when x is 3, my y is 8. Now to graph it, right, let me show you how this is graphed. If you notice, if we pick any numbers less than the -2, it's going to give us, something like, in the shape, but the least negative is going to get closer and closer and closer to the x-axis, but it will never reach it. That, therefore, it's useless to use like -3, -4, and -5, because eventually it'll be real close to the x-axis. That will even be, it will even be hard to graph those points. That's why the wise choices are really from -2 to about 2 or even 3, right? But if we use 4, right? Say we use 4, right? F of 4 will be 2 to the fourth power, will give us 16. So 16 more likely is going to be off the grid. That's why this is the points for x. The numbers for x that we use, that are more commonly used. Okay. Now when x is -2, right? my y is 1/4, it'll be about here. When x is -1, the y value is 1/2, so it'll be about here, 1/2. When x is 0, my y is 1. When x is 1, my y is 2. When x is 2, my y is 4. When x is 3, my y is 8, about right there. And if it was 4, the 16 will probably be about way up here. Okay? Now, exponential functions graph continue. Again, we have f of a to the x, right? So this is like the concept between, it's called exponential growth and exponential decay. Right? If a is more than 1, right? If the base is more than 1, it's called exponential growth. And these are my characteristics. The graph is above the x-axis, like here on the left. Number 2, the y-intercept will always be 1. The graph climbs steeply to the right. Right? As it goes to the right, it goes steeply. The negative x-axis is a horizontal asymptote. This will be my horizontal asymptote. It will never reach the x-axis on the negative side. The larger the a, right? The larger the a here, guys, the more steeply the graph rises to the right. So in other words, the bigger this a, the more the graph goes towards the y-axis. Let me show you. You see that they are. This is y equals to 2 to the 2x, right? Will be something like that in green. Y equals to 3/2, which is 1.5. The graph is something like that, right? You see, the bigger the a, the more it goes towards the y-axis. That's what it means by number 5 here. The larger the base, the more steeply the graph rises to the right. Okay, now what happens if a is between 0 and 1? 0 and 1 or negative, it doesn't matter. So it's called exponential decay. Exponential, right? These are my characteristics. The graph is above the x-axis, right? Everything above the x-axis. The y-intercept is also 1. The graph falls sharply to the right, right? As it goes to the right, it goes less and less. The positive x-axis is a horizontal asymptote. This is my horizontal asymptote, which means the graph will never reach the x-axis on the right side or the positive values for x. The smaller the base, the more steeply the graph falls to the right. And here's what he's saying about this. You see, the smaller the a, right, the more it goes towards the y-axis from the negative side. So these are the characteristics. Now, let's graph number 32, which is g of x equals to 2 to a negative x. So first thing we're going to do, right, we're going to use a property, the negative exponent property, which would be 1/2 to the x power, which would just be 1/2 to the x power. Check this out, guys. By applying, right, when you have a power that's negative, right, this is the same thing as 2 over 1. What's the reciprocal of 2 over 1, right? It's going to be 1/2 and it becomes positive by using the rules that we use on slide number, I believe, slide number 3. So this graph, g of x equals to 1/2 to the power of x. So again, guys, we're going to pick the numbers from -3 to about 3. So if x is -3, y is going to be 8. Okay, and here's my work. That one is -3. It'll be, right, 1/2 to a negative power, right? We do the reciprocal because the exponent is negative, and then it becomes positive. So it's going to give us 8. You see now, guys, we just repeat the process from all these, from -2 to 3, and this will be my graph, something like this. So the characteristics, right? If the exponent is negative on the base or less than or between 0 and 1, the graph, this is like the parent function, the parent graph. This is the shape of the graph. That would always be like this, something like this. Okay, now comes the logarithms. Okay, now, until development of computers and calculators, logarithms were the only effective tool for a large-scale numerical computation, but no longer needed for this purpose. Why? Because we have calculators, we have computers, we have so much of stuff, right? I mean, technology that we don't use this anymore. But let me show you how it was used. The definition of logarithms to the common base 10. Okay. You have y equals to log of base 10x is the same thing as y equals to log of x. because we know if there's no base, we know it's 10. For example, right? If you have x, right, isn't it the same thing as 1x? But we don't say 1x, we just say x because we know there's a 1 in front of the x when we just say x. Same thing here. If there's no base, it means it's base 10, which means what base to the y power equals to the x. That's really the meaning of, behind it. Get no base, right? It's base 10. Okay, now here's how we do it, okay? Let's do this. Here's how we read it. To what exponent must 10 be raised to get x? Okay, for example, what's my base? My base is 10, right? 10 to what power is 100? That's the way you will answer these. So the answer will be 2, because 10 squared will give us 100. The answer is 2. Now log base 10, 10,000 equals to what, right? So this will read as 10 to what power gives me 10,000. The answer is 4, because 10 to the fourth power will give you 10,000. My base right now, my base is 7. So 7 raised to what power gives me 49? The answer is 2. Why 2? Because 7 squared will give us 49. Same thing with log base 3 of 27. It'll be 3 to what power gives me 27? So the answer will be 3, because 3 cubed will give us 27. Okay, now guys, we're going to be writing exponential equations into logarithmic equations and vice versa. Example, right? Again, the definition of logarithms to a base a. Right, so this means logarithmic form, and on the right, exponential form. So we're going to go, going back and forth. For example, write each logarithmic equation into an exponential equation. So now, right, so they're going to give us a logarithmic, we have to put it in exponential form. So here we go, right? So this is a rule, guys. We're going to go from here to here, right? So let's see what the a is, right? My a is equal to 9. My x is equal to 81. My y is 2. So it's going to give us a is going to give us 9 squared equals 81. You see, because my a is 9, my y is 2, and my x is 81. Now we're going right. Now I want you to go the other way. I believe with one example, I think is good enough. But maybe next time I'll put more. Okay, because this is self-explanatory, but just knowing what the a, the y, and the x are for both the log form and the exponential form. Okay, now we're going to go from exponential equation to a logarithmic equation. Right, so we have to know what the a is, what the y is, and what the x is. My a is 5. My y is 3. And my x is 125. So it's going to give us what my y is 3. So it's going to give us 3 equals to log of 5 of 125. Or it can be log of base 5 of 125 equals 3. This will be the same thing. Okay. Now, graphing logarithmic functions. Okay, now, in order to graph without a calculator, you must convert the logarithmic equation into an exponential equation. That's always your first step. Right, so we have to use from logarithmic is equivalent to a to the y power equals x. These are equivalent. This is called logarithmic on the left and exponential on the right. So what did it ask you to graph? Y equals to log of base 2x. Okay, so let's convert it to exponential. It's going to be 2 to the y equals x. And we use similar values as we did for exponential, right? But we're going to use, instead of plugging in on x, we're going to plug in for y because it'll be easier to compute. Okay? So we use, if you notice, we use the same values, -2, -1, 0, 1, 2, and 3, but we're going to plug them in for y instead to solve for x. Right, so if we do that, this is my result, right? Because again, going back to, if we plug in -2 for the y, it's going to give us 2 to a -2 will give us 1/4. If we plug in -1, will give us 1/2, and so forth. Now, the one in blue is called the exponential graph. The one in red is my logarithmic graph. These two are called inverse of each other, but we don't cover inverses in 1324. We do them in 1314 and in the majors that are going towards math or engineering, but not in this class. But these are called inverse of each other. Okay, and the log is in red. Okay, now this is how you apply it in a real life situation. Okay, this is number 36. It says the assets in billions of dollars for a prudential financial incorporation can be approximated by the function a of x equals to 315 e to the power of 0.056x, where x corresponds to the year 2007. Let's find the assets for the following years. Okay, so the key word here, guys, is x equals 7, means the year 2007. Okay, so if we're looking for part A, right, since the year 2000, right, so then x equals 0 corresponds to the year 2000. And for B, x equals 12 corresponds to the year 2012. So for part A, we're going to evaluate the function at a of 0, which will give us, right, then here we apply the rule, right, e to a 0 power, like any base to whatever to a 0 power will always give us 1. And the answer will be 315. So it'll be $315 billion because the answer is that the assets are in billions. That's why it'll be 315 billion. Okay, now it's always good to know that when the time is 0, the 315 will be the initial value, and it's good to know for the next problem that we're going to be doing. But let's finish it off with B now. So we're going to be evaluating A at 12, which means I'm going to plug in 12 for the x's. And all we do is use your calculator, and you get your answer. So it'll be about $616.8 billion. That's the answer for B part. Now comes number 37. I believe this is the last one. Okay, we're going to finish a little bit early, just in case you have any questions. Okay, now, hey guys, during in 2020, right when COVID started, I think we were right before we went to spring break, right? That was when COVID started, like in February here in the United States, or like late January. So I got the info from the news, and I show my students how simple it is to get an exponential function. And then this way, once you get the function, it'll be easy to estimate or kind of predict how many people will be infected, or whatever the situation is, that you're trying to find an exponential function for, you'll be able to use these type of functions to estimate how many people will be infected at any given time. And I also use one for the gardening club because I have a garden there at Trans Mountain, and we did some to how many plants would it be at any given month by using these type of this type of formula. But anyway, here's how we find the formula here, guys. It says a deadly virus has affected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to 128. For part A, find the model of the form y naught, f of t equals to y naught b to the t, with t equals 0 corresponds to the end of the month of January. And then for B part, if the trend continues, about how many people will be infected by the given year. Okay, now guys, y naught is the initial value. Remember right now when I said earlier, guys, when I said when t was 0, the y naught will be your initial value, and the b is my base. Okay, here's how we come up with the formula. We need to get y naught and b. Okay, y naught is the amount present at time equals 0. So here, right, so before it says here the daily virus has affected the world. At the end of January, there were 2 cases. So when they started this getting this experiment, right, or trying to get the formula, when they started, right, there were 2 cases. So my first point will be 0, 2. Y naught will be 2. And then it says by the end of April, right? It had grown to 128. So here's where you find what time was at the end of April. Since t equals 0 corresponds to the end of January, then t equals 1 will be the same thing as February. T equals 2 was equivalent to March, and t equals 3 corresponds to the end of April. Right, so we can go, right, so there were 128 cases at the end of April. So we can go straight from the beginning, right, to the end, right? I mean, the t equals 1 and the t equals 2, I just did that so you guys can see exactly how it went from t equals 0 to the end of April, because here, guys, will be my second point. Let me show you what I'm talking about. The second point is going to be 3, 128, which means f of 3 equals to 128. Okay, now we're going to plug everything into the formula to find the b. Check this out. Here, guys, right, my second point is the x value is 3, or the t value. Here they're not using x, they're using t. So 3 is my t, and 128 will be my y. Is equal to 2, right? My base is 2. My y naught is 2. And we're looking for the base. So here, what we're going to do here, we're going to divide both sides by 2 because we're trying to solve for b. It will give us 64 equals to b cubed. Now, we have to get rid of the 3, the exponent, so we do it by applying the power rule. Right? How can we cancel the 3, right? We're going to raise both sides to the power of 1/3. Right? Now here on the right, we apply the power rule, right? A power to a power, we multiply the powers. This will give us b equals to 4, because 64 to the power of 1/3 is equal to 4. Okay, now how do we know that? Okay, this you can convert it from exponential to a radical, or you can use your calculator, right? Most calculators, they don't have to the power of 1/3, right? So this is that's what most calculators, they don't have the cube root of 64. That's why you have to convert it to a radical, to an exponential. That's why the 1/3 is the same thing as the cube root of 64, right? But again, the cube root of 64 cannot be entered into mostly all the calculators. That's why we have to convert it to an exponential. So 64 to the 1/3 power will give us 4. Just put 64 in your calculator, you're going to raise it to the power of 1/3, and it'll give you 4. So we got my y naught, which is 2, and we got my b is 4. So now let's plug him into the formula. So this is the answer for a part. F of t equals 2 times 4 to the power of t. Now let's find b. Right? So from the it says here, if the trend continues, how many people will be infected by the end of the year? So from January to December is 11 months, right? Because from the end of January is where we started. Another way to the end of December will be 11 months. So for part B, we're going to evaluate the function at f of 11, which means all we do is plug in 11 where the t is and put everything in the calculator, and we get our answer. This gave us like 8,388,608 people will be infected by the end of the year. But that really was not the case, here in the US. Why is that? Because this way scientists and biologists, they became this, and they began using like a lot of what's it called? The right word, intervene. By that, they use masks, social distance, wash your hands, and all that stuff. That's why it limited the people that got infected. Imagine all those people that don't have good hygiene, like in Africa and stuff, or those poor countries. That's why a lot of people died all over the world, because some of them didn't have the equipment as what we have here in the United States. Anyway, this is how you use exponential functions in real life, and I believe we're done with this workshop. Let me go back to the host so they can tell you more about what's going to come next week. In the meantime, if you have any questions, please let me know, and we can answer your questions that you might have. Thank you.
Thank you, Mr. Sassi, for your wonderful presentation. We wanted to remind you guys about the previously recorded sessions, which are available on the YouTube playlist. The session will also be available on that playlist later today. At 1 p.m. today, we will have a presentation from the Writing Center and CSD, and we will be back with Happy Math Hour next week at 11 a.m., where Math 1314 will cover synthetic, division, and complex numbers, and Math 1324 will cover solving exponential and logarithmic equations. Our 1 p.m. session next week will be a presentation with the Veterans Resource Center. Thank you for coming in today. We hope you all have a lovely weekend. If you have any questions, feel free to use the chat box or your mic. We hope to see everyone again for Happy Math Hour.